So thank you very much for the introduction, and it's slightly strange feeling to arrive late and to be to be the first speaker of while participating at the conference. I try my best, given that I just spent 16 hours airborne, and also I had a cold. I made a COVID test before flying, and it was negative, fortunately. But if I cough, maybe I will put on my mask again. So the title indeed is about has to do with random tensors. But today I will probably not speak too much about random tensors, and kind of start with some motivation. So what I would like to talk about during this first lecture is about single random matrix models versus multi random matrix models and symmetries. So random matrix models, very soon they will end up. So the spoiler and the relation with what I'm going to, with the title, is that very soon the matrices will belong to this kind of spaces, and the symmetries will come from tensors. But I would first like to start without this and symmetries. Be something like a unitary group tensor. So here I would have a D and a D. So, but that's for later. And so, so in general, again, it's possible that something which I'm going to say will be very boring for people who have already heard free probability theory. I'll try my best so that everybody gets something out of the story. So initially, in random matrix theory, the way I understand it, originally, it was the study of a single matrix model, and that would typically be denoted by something like this, xn. So xn is a random variable. This is a matrix valued random variable. And what we do is we consider the sequence indexed by the dimension, and we try to understand what is the behavior as n goes to infinity in the large dimension limit. And of course, since the space keeps varying, one has to put everybody in the same space first. If one wants, like, if one has a probabilistic point of view in probability, one would like to prove some limit theorems. So for that purpose, everything should be in the same space. And typically, so today I will mostly focus on the case where the matrices are self-adjoint. In this case, we could not denote by λ1, λn their eigenvalues. These are the eigenvalues x. And historically, the kind of that you would like to understand is the distribution, like the spectrum, the histograph, the eigenvalues, let's say, which you could view as a probability measure like this, 1 over n, sum for I between 1 and n of a Dirac mass I, and then we would like to understand how this is a probability measure. So this would be a random probability measure. We'd like to understand how it behaves as n goes to infinity. And so here I don't clarify yet what I mean, but depending on the cases, this could be something like maybe this could be some almost sure convergence, some convergence in proba, maybe some convergence in expectation. There are lots of possible cases of interest, some which are stronger than others. And I would say that this has probably been mainstream in the mathematics aspects of random matrix theory until the maybe 70s or 80s or so. And well, multi-matrices, what would they be? So here again, maybe this is a slightly personal point of view which I'm proposing. Multi-matrices. That would be what? That would, instead of taking just one xn, I would take a d-tuple x1n xdn. So now all, as before, these are n by n matrices. So this is actually, this is an element of MNC d-tens. So this is a random variable which has values there. And then you could, then the question you want to ask is, what is the behavior of this as n goes to infinity? Of course, there is a cheap answer to this, which is, you could just put them in some bigger matrix, each block on the diagram, and then you could say, well, it's a bigger matrix, and I can give the same answer, but that's not an interesting answer somehow. It's like here, it's kind of natural for some reason, which I will describe later, why it's interesting to study these observables of a matrix. So here you would like to study some other observables, and typically, if you want to stick with this idea, somehow what you would like to do is, if you want to understand the behavior, typically. What you do is you should craft a random matrix model out of x1n xdn. And so I would say here a single, so just one, just somehow get back to here, and check its convergence in the single random matrix model setup. So here by craft random matrix model, what I would mean, probably the most basic example would be to, for example, you could allow a plus multiplication and scaling. So which means, you take a non-commutative polynomial in the HCIZ. So for example, let's say I want to study this x1d, x2d plus x2d, x1d. And that's one single random matrix model. And I would like to see if it converges. So there are many ways of defining a convergence, but in general, I think it's kind of correct whenever one looks at the papers, the way they are written, that when we have multi-matrix, we decide some kind of operations which are legitimate, and we would like to be able to show it for if it converges for all possible craftings. So that here is what I would call what was really investigated in depth in free probability theory. I'm not going to speak, almost not going to speak about free probability theory, which was invented by Voiculescu in the 80s. But he invented it with absolutely probably no knowledge, and at least no motivation for sure in random matrix theory. He only noted in the 90s, actually. He only noted in the 90s that there is a relation with random matrices. And right, so it's kind of natural to do this, but there are many other things which you could do, and here you could also, for example, allow in addition, to take some smooth functions. Functions which are reasonably regular. So this has been done by many people. I'm not going to, Hagrup and Torgersen did a bit of that. Lionni did a bit of that. Parodi did a bit of that. Many people did things about this. I will also add here, for the purpose of trying to give a coherent picture, that it would be actually quite natural to add the inverse to this picture. So let's say I allow to take inverses as well. Maybe it won't be invertible, but maybe it will be invertible with probability 1, things like this. And that actually has been studied heavily by many people, including people here. So I think this was, from the abstract point of view, it was started by Speicher, by Roland Speicher, but there was also Mai, Yin, and I also did some things, Miyagawa also. So we have more matrices, and we would like to see if with more matrices we can obtain infinitely many asymptotic behaviors for infinitely many single matrix models obtained out of some allowable rules. And of course, if I say it without any precision, you could say, well, okay, so I should, like, I've never spoken about the laws yet, so I should speak about the distributions. And so what is the relation between the xi ends. So so for me, I'm just going to assume that for us, I'm just going to assume that they are independent. But there are many other very interesting things which can be done. Which actually I think could be of interest to some people in this audience. So other cases of interest would be to take some potentials. So instead of taking like I tweak the independence by introducing potential and try to see what happens when I do this this kind of things here. And so yeah, maybe I should also have said that perhaps maybe I've been a little bit too general right away. I think probably. So this is what I call anyway. This is what I call a multi-matrix model, and one original motivation for considering multi matrices, and that's also going to be that was a very heavy motivation of Razvan, Luca, and I when we started our project, is to try to understand what is the distribution of x1d plus x2d. If I have two matrices and somehow I know something about the spectrum of one matrix, something about the spectrum of the other matrix, what is the sum of what is the spectrum of the sum? So the collection of all possibilities is known as the Horn problem. And so if I have some randomness, maybe you could say this is some random some random Horn problem. So even just to start worrying about these problems, you already need some multi-matrix model somehow. So in this case, so see, that's also perhaps the reason why, if I say that multi-matrix model started in the 80s, that's an overstatement, because these questions have been studied earlier. Yes. So yeah. So here, for example, see here you have a probability measure. You could ask if the probability measure converges. So here you could ask if the probability measure of this, if you take the eigenvalues of this guy, like here, converges. So I'm actually describing, it's not exactly the way Voiculescu did. Voiculescu was working directly with the moments somehow. There was some kind of reasoning that knowing this is equivalent to the moments, knowing the moments if this is bounded. So this is actually equivalent. It's maybe not a standard way of printing things, but yeah, that's that's equivalent. And so what actually, yeah, that's I mean, since you ask it, I think I was planning anyway to specify that. So what does convergence mean? I'm going to write down basically the answer to to your question. So initially, I mean, I think historically it is correct to say that this is what is meant somehow. I think that historically both Wishart and Wigner, they were interested in the eigenvalues in distribution, but you have many other potential cases of interest. So you could have the moments, or maybe the mixed moments. Okay, mixed moments, which would be something like this. Would be how to understand something like trace of x I1 and x I2 and so on and so forth. And how does it behaves as n goes to infinity? Or you could also have something like so I'm not going to speak too much about this, about the Stieltjes transform. Maybe you would like to understand how it behaves in a compact neighborhood which does not touch the real line or something like this. And you could also have, I mean, something which I have been interested in as well is how does the operator norm behaves. That's also something which you could try to to measure. Interestingly, I'm not going to say anything about that today, and probably not during all my lectures as well. It turns out that you could legitimately argue that it looks well, here. It's kind of known that these kind of quantities are actually more or less encompass the same information as that. Here you could argue, well, it looks like it encompasses much less. Like it should be like just looking at the smallest and largest eigenvalue. How on earth could you know all eigenvalues out of this? It turns out that there are some very interesting and very deep theorems in operator algebra which say that some C-star algebras, which actually are closely related to that, I'm not going to speak about it, but have a unique trace. So actually, quite often, knowing the operator norm is enough to do these kind of things. But anyway, yes. Something which is also natural is looking at the correlation. And that will have some relation to second order freeness or higher order freeness, which are some experts in the room. And I will actually say a few things about that later. But first of all, let me tell from my point of view, and I think, I mean, even though it's not really stated that well, I think that's a good convergence theorems in multi-matrix, in a multi-matrix setup. They have what I would call a bootstrapping structure. And by this, what I mean is something like this. It means that if we know that so a statement would typically be like this: if x1 and xdn converges for some meaning which has been defined ahead of time, and x d plus 1 n converges as well and is independent from x1 n x dn, then the n-large family x1 n x d plus 1 n converges. So the idea is that you should be able to start with a family and make it bigger. So you could start with 1. We start with 1, just as in classical, like in single matrix or matrix theory, and then you have another one which is independent, and you know that then the two, they will have a good behavior, which means that I can do any operation which was authorized previously, take a non-commutative polynomial also, and it will converge. And now, if I know that that if I take 2, they have a good behavior, then I take a third one, which is independent, and it will converge, and so on and so forth. So this is typically the kind of results which I mean, I don't know if they are nice, but this is somehow the kind of results which tend to be obtained in this general context. So again, it might look a little bit like I mean, this is not hand waving, of course, because I'm actually stating theorems, but somehow viewing things that way, hopefully, will make what I tried to do with Luca and Razvan nature. So some examples here. Examples would include Voiculescu 92, where he proved that IID GUEs are asymptotically. And I will probably get back to it a bit later, but I suppose I don't have to recall what is a GUE. It's a self-adjoint matrix with IID Gaussian entries, which is properly rescaled. And if there is one, then it had been studied at length. And so he said if I take 2 independent ones, then if I take, so Voiculescu actually proved this statement for this. If I just allow this operation, then the spectra will always converge. Then he proved the same in, I think, in 98. He proved the same with IID unitary invariant. Random matrices. And, well, Nika, Andrew Nika, in, I think, around in 91 or 92 as well, proved the same with IID random permutations. Permutation matrices. Then what else? Well, I'm going to tell more, but Hagrup Tomlinson. In 2004, I think, proved the same for IID GUE with the operator norm. With this property, and so on and so forth. So all results they always had this kind of. I mean, okay, so maybe these two results here, they were not. I mean, technically they have some bootstrapping structure, but like a simple one in the sense that everything is independent. So with Camille Mal, actually, here at the Schrödinger Institute, we proved this extension of Hagrup-Torbenson so 10 years ago for U-invariant spaces. And here, actually, this is exactly a bootstrapping structure. And So the general fact is that this takes me to the second part of the title of the first lecture. So a fact is that the measures of interest the laws, if you want, the measures of random matrices. Okay. So when I say a model, this is a probability measure on the matrices have high symmetries. So typically what it means is that there exists a subgroup, which I will call Gn, of the invertible matrices. And actually here we saw the generality. Well, yes, I'm actually going to assume that this is a subgroup of like a compact subgroup. So yeah, so to be able to deal with probability measure, it would have to be a compact subgroup. So without lots of generality, I can assume that this is a subgroup of UN, up some conjugation. And so there exists a subgroup, so compact, such that the law, the distribution of my xin is the same as the law of G xin G inverse for every G in the group. So the distribution is highly symmetric. This is the case. This is the case, for example, for the GUE. For the GUE, the group UN is an invariant. When you take random permutation matrices, the permutation matrices which are the natural invariant. When you take the Wigner matrices, which I did not introduce, but which is where all this started, it could be for some nice Wigner matrices the permutation matrices with some 1 and -1, which will be some risk product of the symmetry group with C2. You always have symmetries which play. So when I say of interest, of course, that's I mean it's not exactly clear what it means, but this is where we can get interesting theorems, and perhaps where there were some natural motivations. And yeah, so one more thing which I'm going to say is that actually there could be today I stick to the self-adjoint case. All this theory has also like you could discuss again the whole theory without this symmetry, and then it would be natural to have some left and right action which are different. This is very interesting and natural, and actually all what I say could somehow extend, but just to have some unified setup for now, I'm just sticking to that. And so maybe now I'll get back a little bit to that. So natural so in general, so maybe it's too early to. The natural object to study. So studying this 1 over n sum of the eigenvalue counting measure, the normalized eigenvalue counting measure, is equivalent to studying the trace of x n to some power. And why so? This is because, of course, the integral of is because, of course, if I compute this xl d of this with an x, this is equal to 1 over n times this. So studying this quantity is very nature. And a simple fact here is that the collection, the algebra generated by the functions a trace of x to the L is constant on the orbits of the self-adjoint matrices. Well, actually, on the matrices on which the unitary group or any subgroup acts. And it is separating. It is separating for G when Gn is the whole unitary group. So if I know this, I know all the orbits. Actually, this is overkill because I just need to know n of them. But again, if I want to have a unified framework and let n goes to infinity, it's nice to to have this. So that's also somehow one point of view is that studying the limits, maybe I should say the behavior as n goes to infinity of the infinite family of random variables of real random variables, trace of x n xn L is nature. And somehow this is the so studying the behavior here. What I could even say is the law. So we could look at these families and their expectations, but we could also take any polynomial in these variables, and this would be actually two different problems. And this is actually the approach that we are taking with Luca and Razvan. And can I do it without water? It's better to do it with okay. Okay. Need to. So I don't. I had arrived earlier, I would have studied. Yeah. The unitary group. Unitary group. Yeah. So here you see, I'm just. This is a very pedantic way of saying that that the orbits are described by the eigenvalues. But but actually, this is the point is that very soon we'll be interested in some groups which are much smaller, which have a tensor structure, and in this case, the natural interpretation of random eigenvalues disappears somehow. So we are kind of forced to look into that. I have to and so let me yeah. So let's see. Yeah. So maybe okay. I will make this remark. Just to actually to follow up on your question, remark. So when I say separating, you could say that this is what it means is a complete invariant. Okay, is a complete invariant. And what we have is that this family is not a complete invariant. For example, if in the other case which I discussed a bit, if Gn is the permutation matrices, and in this case actually the complete set of invariants. In this case, the complete set of invariants is called the traffics. I mean in algebra, sometimes it's called the partition algebra. But from the point of view of random matrix theory, this is the traffics, and this was heavily studied by Camille Mal and Guillaume Sebron, Benson O, and many others. So they have made lots of very interesting things. One point, so there's strictly more invariants, which is of course normal, because if the group is smaller, then you should expect to have more invariants. But however, there is a phenomenon which would be of interest to us as well, which is that even though you have more invariants, just this family of invariants is already interesting per se, in the sense that as I actually, I don't even have to write it, in the sense that Nika proved that random permutation matrices are asymptotically free. So random permutation matrices, they have this symmetry invariant. However, if I just asymptotic freeness tells something about that, and even though in principle you need more invariants, if you just declare that you are happy with less invariants, then you can bootstrap out of an incomplete set of invariants. So there is this phenomenon which was perhaps anecdotal, when stated, but which is actually quite critical from the point of view of what Luca Razvan and I are trying to do. So what I would like to do is to give the the case of describe more at length the case of G n is un. So, so again, what I'm saying is I have the matrix x1 n, x2 n, and so on and so forth, which are independent, and they all have a distribution which is invariant under unitary conjugation. So you could like people who are experts here could say, well, this is asymptotic freeness. We know it, and that's kind of true. But there is a small caveat which I want to point out, which is again as a motivation. So we are going to static case. So we are going to assume that the matrices xi n are independent, and we'll assume, as I said, that the distribution of xin is the same as xu xin u star, and they are all self-adjoint. This is for every unitary element of the unitary group. And in addition, I'm going to assume that so for all I and for all L, the expectation of the trace of xi n to the power L is, I will first write it like this, big O of n, and the covariance, I would put an L and an L prime, the covariance of a trace of xi n to the power L, trace of xi n to the power L prime is, so here we'll say small o of n squared. So this is a bit less than the product of these two things. So there is some kind of concentration which occurs, and then okay, maybe I was hoping this would dry, but I didn't calculate correctly. So then, well, I will just say it in one word, hoping that what I said before was clear. I mean, if it was clear, what I say here is rigorous. So then, bootstrapping holds, which is that if I take any word in these things, it will satisfy this property, and same here. So if I just have like x1 to some power, x2 to some power, and now if I take like x1, x2, x1, x3, whatever, then the same property will hold true. And same here. Then bootstrapping holds. And if I was slightly more precise, so here I will do, here being more precise would be to say, so here small o, so there is no way I could be more precise, but here it would mean something like this behaves like n times some function. Presentation I took, yeah, of I and L. Then bootstrapping holds, and this is the same for the blue version. So if I just know that this is bounded, then any word will remain bounded. And if I know that it has some behavior at n goes to infinity, then any word has some behavior as n goes to infinity. And in this case, so maybe I'll write it down. So it means that expectation of trace of xi1 and xi2 and xiln, it will behave like n times some function which depends on the sequences I1, IL, and on all the FIL. It's a very complicated function, but it's explicit. There is an explicit way to compute it. And how to compute it, actually, this is well, the algorithm was given by Voiculescu, and elegant ways of calculating this were given by Speicher, and then by many other people subsequently. So here, on purpose, again, the free probability people here could ask, why didn't I normalize the traces? And that's, of course, on purpose. This is because now, let's see. Right, so maybe I will try to play with colors. So now let's look at some. No, maybe I won't try with. So now a variant of this will be, I'm going to assume now that expectation of trace of xi n to the L is now small O of 1, a big O of 1. So here, and again, it could have any fluctuation, but I will assume that it has some given fluctuation at infinity, so that it behaves like f of IL. And for the covariance, I'm going to assume that this is small O of 1. And then again, bootstrapping holds. In the sense that expectation of trace xi1 and xiln behaves like some function of I1, IL, and of the FIL. But the important point here is that this is a difference phi. Two things are different. So this one actually comes from a free convolution. And this one comes from cyclic Boolean free convolution. So if one somehow, if we do random matrices, it's kind of natural to say like the trace would be of order n, or of order 1 over n, something like this. I mean, because you have some norms in mind. But when one does tensors, it's less easy to do so it's better to be agnostic about which behavior to take. And in this case, somehow more phenomena occur. And so this actually was studied not so long ago. This was studied maybe in 2015 or so by myself and two Japanese collaborators, Norioshi Sakuma, Takahiro Hasebe, and Norioshi Sakuma. And something interesting which we had not noticed. So here you see I should have put yeah, FIL. Okay. If actually here we had put instead some n to the power alpha and some n to the power alpha here, with alpha, which is a number between 0 and 1, then the result would have been unchanged. So somehow, this somehow is result for alpha equals 0. So you could see that this is the result for alpha equals 1. And the fact that for alpha equals 0, 1, nothing changes was actually observed in the paper with Lionni, with Gurau and Lionni. And here somehow, like the trace behaves like something. Well, it's kind of natural to make such an assumption, and you only have one choice for the parameters of alpha, because you have, if you have unitary invariance, then you have only this family to study. You don't have too much choice. But again, I keep teasing things. For higher tensors, then everything breaks down somehow. Like here we have much more choices and much more possibilities which show up. So yeah, so when we go with tensors, I have to say which is the group first, and then what are the invariants. But the invariants, they behave to n to something. The something, there are many possible choices of interest which will give many types of convolutions. And actually, well, Luca, Luca is the real expert actually. But there are many. I'm not sure that we have completely sorted out all the possibilities in all the cases. There are many non-trivial things which happen. And well, okay, so it's kind of time already. So I've done 70% of what I wanted to do. Let's see. So maybe I could just explain. Yeah, so exactly. So the plan somehow, so the plan now is, so the plan is how to what about other GNs. And so today I have described only UN and to some extent the symmetry group, where I have said one word about the risk product. Maybe tomorrow I could say briefly something about ON, because Jamie is an expert here, and there are many very interesting things which happen when we take the orthogonal symmetry. But I will spend lots of time actually on working on GN, which is, so I will spend a bit of time on working on GN, which is UN itself, but through the embedding that U is sent to U tens D in the D-fold tensor product of matrices. I will spend a bit of time on this, and I will spend more time on GN, which has the structure of a group as a group of UN D times, where U1, UD are sent to the tensors, to their tensors, U1 tens UD. Again, in M, N tens D. So now we're looking at some N tens D matrices, and the invariants, they are what are called local invariants in quantum information theory. So I have a tensor structure, and I don't have global invariants, I just have local invariants. So you could, from a point of view of group theory, you could say that here you have less invariance than here. So here you also have less invariance somehow, but the invariance is just local here. And there are quite a few things of interest which happen in this case. And I also wanted to speak today about the fluctuations, because here I was very loose about that. The fluctuations are also a very important part of the study. So we'll say something about that, and understanding all that. So basically, the interesting phenomena appear thanks to the symmetries, and to prove any results, we need to be able to integrate over measures which have symmetries, and this has to do with Weingarten calculus, about which I'm going to say a few words as well. So that's what I'm going to spend. I will continue tomorrow and Thursday along this outline, and I stop here for today.